Okay, this video is going to look at nuclear energy. And of course, nuclear energy is energy derived from nuclear reactions. And what we have in nuclear energy is we have a nuclear reactor, which contains nuclear fuel. It has certain pipes so that control rods can come in and control the rate of the nuclear reaction. This is a chain reaction and it can go on uncontrollably. Then you have the nuclear reaction produces heat, and this heat can be used to heat up water to very high temperatures. That's number two, the steam generators. So these steam generators produce steam, which goes through steam pipes and goes to a turbine. So 5 is a turbine, which spins. And the spinning of the turbine goes to a generator, which produces electricity. The electricity goes to an up transformer. So 7 really is an up transformer, which increases the voltage of the electricity. So it can be carried by high voltage power lines, which is here. And in fact, before going to buildings and so on, you need a down transformer, which lowers the voltage to safe levels. And of course, the water here can go to a cooling tower and be given off as steam. Some of the water is released, and some is recycled. And this is the basis behind nuclear energy. So, what we're going to look at in this class is nuclear power. We're going to look at nuclear fission and nuclear fusion. Use of nuclear fission, nuclear power plant. The nuclear power plant basically is that. And the nuclear fuel cycle. So fission, first of all. What happens in fission? And this is a large nucleus, such as uranium-235, is broken down into smaller molecules, atoms, such as krypton and barium. And what happens is a neutron will bombard the nucleus, and this makes it very unstable, and therefore breaks down into more atoms. So notice a neutron will bombard a uranium atom, and it produces a very unstable uranium-236 atom, which breaks up into a barium and a krypton atom, and also gives off 3 neutrons. And these 3 neutrons can then bombard further uranium atoms. And that's why we have a chain reaction. And the reaction can become uncontrollable. And that's why we need control rods to absorb these neutrons at given points in time. So the rate of reaction can be controlled, so that a steady amount of heat can be given off only, and you don't get a nuclear reaction occurring. So as I said, the neutrons produced can be used to bombard further 235 nuclei, initiating a chain reaction, and this liberates vast amounts of heat. And in the nuclear reaction, control rods can be used to absorb neutrons, and tends to reduce the rate of reaction and prevent the reactor from overheating. We also have fission. We could have a deuterium atom and a tritium atom coming together and forming helium and a neutron. And this is a sort of reaction which occurs in the sun. And it gives off vast amounts of heat, which could potentially be used as a source of energy. Although such technology has not been developed yet. So with sufficiently large and sustainable energy profit, fusion could be used to generate electricity commercially. The main fuels used in this nuclear fusion are deuterium and tritium, which are both heavy isotopes of hydrogen. And normally fusion is not possible because of the strongly repulsive electrostatic forces between the positively charged nuclei prevent them from getting close enough. Of course, such reactions occur on the Sun because the gravitational force there is very, very strong. But normally we don't have it, and therefore this reaction doesn't occur normally. And therefore, currently there's no commercially available energy this way. Although it has advantages because the products are helium and neutrons. The helium, of course, is not radioactive. So it's really, if we could use it, a much cleaner form of energy than fission reactions. And we ought to know the structure of a nuclear power plant, where we have a containment center, which will have control rods, and the control rods can go into the nuclear fuel and into the nuclear reactor C. They produce heat, which is seen in the steam generator. And the steam generator produces a steam line, which goes to a pump, which goes to a turbine, which spins, going to a generator that produces electricity. Electricity must go to a transformer, which increases the voltage of electricity so it can be carried without much loss. And you have a cooling tower. Knowing that structure is important. And that's basically what a nuclear power plant looks like. We have cooling towers here. Not sure where the reactor will be, whether it's here or probably here, is where you'll find the reactor. So you can watch these two videos for you to watch, and you should watch them in your own time. So, advantages of nuclear power: low operating costs. It's climate compatible, meaning it doesn't contribute to climate change, and that's a really big advantage. In order to stop climate change, one alternative is to use nuclear power, and it helps countries to grow economically, because once you put the nuclear power plant in place, the operating costs are low. So nuclear energy may be used in a range of methods, and the power production is very reliable. But of course, it has a high investment. The initial investment is quite hefty. It's a high capital expenditure to get it started. And although it doesn't contribute to climate change, people can be exposed to radiation, and they have serious health issues, such as cancer. And of course, it can induce mutations, and therefore children can be born with diseases and so on. Okay, with nuclear electricity, there are long-term storage expenditures to contemplate. It can produce a large amount of electricity very quickly, but we therefore probably need storage devices such as large batteries and so on, so that energy can be stored during non-peak hours. Another disadvantage is uranium mining is vital to keep nuclear energy market viable. And there's only certain places where there is suitable nuclear material. And of course, transporting nuclear material is sometimes problematic, and constructing a new nuclear power plant can take a long time. I suppose also there might be interference from foreign countries. For example, the USA does not want Iran from developing nuclear power, because if they're frightened, they might use the nuclear material to make bombs rather than electricity. So there's involvement of foreign powers which might not be desirable. But also disposal of nuclear waste, which is very harmful to the environment. And there's a danger of nuclear accidents. Then you have the nuclear cycle. What happens to nuclear ores? We start with the natural material, which is slightly radioactive. We need to mill it into a powder. And then we need to convert it by enrichment, normally by centrifuge, where it can be then made into a suitable material, kind of fuel rods, which will then go to a power plant to produce electricity. Some of the nuclear fuel has no use, and therefore is spent, and some can be reprocessed. So you have a cycle occurring at this point. But the spent fuel has to be disposed of. So, first of all, we have to process the ore. And uranium ore is mined, milled, and converted to its oxide, which is U3O8. And we call this yellow cake. And the process involved in this step produces large volumes of tailings that are only slightly richer in activity compared to the background radiation. The waste is called naturally occurring radioactive material waste, or norm waste. And norm waste streams are handled like other high-volume tailings with special considerations of their slightly elevated levels of radioactivity. In the process, radium and its disintegration product, radon gas, are produced. And both radium and radon are radioactive. And proper measures need to be put in place to control them. Then the enrichment, the yellow cake, which is 235, is fissionable isotope and is used for production of energy. To enrich the yellow cake, this isotope, a gaseous diffusion plant can be used in which uranium is converted to UF6 gas and then allowed to diffuse through several metal barriers. And then uranium-235 diffuses to a slightly higher rate than uranium-238, and enrichment can be achieved in the plant. An alternative method is to use a centrifuge, in which the centrifuge forces differential separation of uranium-235 from 238, and both processes require cyclic operations to carry out enrichment, and significant amounts of waste are left over that contains UF6 in the first case, and U3O8 contain material in the latter. So, continuing. The fuel fabrication and power generation. The next step is to convert the enriched UF6 to uranium oxide, UO2. The oxide is then cast into pellets to be introduced as a fuel, which is done by stacking the pellets in zircaloy tubes and producing fuel rods. These fuel rods are gathered in a fuel assembly, which consists of zircaloy shroud, or can be wrapped. And the assembly is loaded in a core of a reactor to conduct controlled nuclear fission. And during the fabrication step, machining and machine shop waste is generated, which contains traces of radioactive metal. And this becomes part of the solid waste generated in the nuclear fuel cycle, which we mentioned. Then power generation. During power generation, fission reactions produce power at the cost of enriched components of uranium, and in the process they also produce large numbers of radioactive isotopes. These include isotopes of uranium and the elements of actinide series beyond uranium, such as Pu and transuranium elements, and the transuranium elements are called PRUs. They also produce isotopes of cesium and iodine, and those of metals such as strontium, barium, and an isotope which has no natural analogue called technetium-99, which is produced only in nuclear reactions. And after a decade of using these assemblies, the rods become depleted in their activity and must be replaced or reprocessed. And the main fuel has been depleted and its activity is spent fuel. So the fuel rods need to be replaced every so often to get new sources of the fuel. Then fuel reprocessing. The spent fuel may be reprocessed to enrich it. And in the reprocessing step, highly active isotopes may be separated from the fuel, such as fission products and plutonium, which may be used again in the reactor. And reprocessing waste becomes part of the waste inventory and needs to be treated for disposal. Safe storage of spent fuel, either reprocessed or otherwise, is a major concern of nuclear industry. Through the activity of fuel rods is depleted after the use for a decade, and they cannot be used in a reactor. They are still hot. They irradiate neutrons and gamma rays, and that's what we mean by them being hot. To suppose sufficient danger of runaway reactions is stored in close proximity to each other and in sufficiently large numbers. As water is a good absorber of neutrons, the water pools are used to store hot rod assemblies till their activity is sufficiently diminished, so they can be transferred to dry casks and transported to interim storage. And for permanent storage, they need to be encapsulated in a suitable shielding matrix and sent to repositories. And the bulk components of the end-use waste streams consist of hardware, including zircaloy framework, contaminated facility parts, and worker outfits. Most components in this category are unreactive in the acid-base reactions used in forming CBPCs, and therefore one can expect good macro-encapsulation of these components. However, they are also insoluble in groundwater and hence non-leachable. They are therefore of least concern in the entire immobilization scenario, and they are microencapsulated in a suitable matrix and isolated. And CBPCs provide a dense and durable matrix for this purpose. And this basically finishes this discussion.